Welcome to the 6th of 7 lessons that we have here on assessing the accuracy of remotely sensed data. Okay, so this is part 6. In part 4 and 5, we talked about thematic accuracy. First, we looked at an overview. Then we looked at more of the sampling considerations and other considerations. And in part 6 here, we're going to look at methods and analysis. So I'm Russ Congalton, and I'm glad that you were able to join and listen to this lesson today. So what are our objectives? We've got 5 objectives. First, we're going to make sure you understand why I don't like the term ground truth. Then we're going to discuss some different types of analysis. We're going to review the descriptive statistics that you can generate from the error matrix, make sure we're okay with that. So all those things are sort of review. Then we're going to get into 2 basic analysis techniques, Margfit and Kappa. And then lastly, I'm going to provide a little bit of an introduction to 2 different advanced analysis techniques that you might be interested in. One called fuzzy accuracy assessment and the other called change detection accuracy assessment. So let's get into it together. So you've heard me say this before if you've listened to either the introductory 2 lessons that I did or these 7 more detailed lessons on accuracy assessment. I'm on a one-person campaign to remove the term ground truth from our vocabulary. I just don't think it's appropriate. When you go to the ground, it's often true that a bunch of us would disagree. We would not agree what the label is supposed to be. And so I think it's a misnomer. I think it's an inappropriate term to use. Yes, reference data is supposed to be more accurate than the map that you're assessing, but it's never going to be perfect. It would be great if it was perfect, but nothing's perfect, okay? And so I much prefer the term reference data or ground data or field collected data or whatever. And especially if you've collected it from using some manual interpretation of high resolution imagery, okay? How can you call that ground truth? It's not even from the ground, okay? So it's just a poor term. Please help me out. I would appreciate it a lot. No more ground truth in your vocabulary, in your writings, nowhere. That'd be great. Okay, different types of analysis. As we've mentioned earlier in these previous lessons, you can do non-site specific assessments and site specific assessments. And so just to make sure we're understanding that early on in accuracy assessment, and still in some places, people do non-site specific assessment. The issue here is that there's no locational component. What happens is it does an average by hectares or by acreage, by category, and it compares what the map said in an overall total to what the reference data said in an overall total. Good examples of that are, the amount of corn grown in, some county in Nebraska in the summer of 1982. Okay, so what do? They have some reference data that they use. Maybe the Farm Bureau or somebody has collected that amount of corn that was, brought in for sale, and then they've got a total acreage. And so the farmers all get together and say, yes, we grew, 4,782 acres of corn. And then somebody makes a map of that county and they grew 4,444 acres of corn. And it's a non-site specific assessment, okay? It didn't last very long. You can see that there's some power in that. It gives you an overall feel for how you're doing, but it doesn't give you anything about the exact locations. And the first thing we really want is, okay, how did I do right here? Okay, what about my house? What about my property over here? So we need to get to site-specific assessments. So site-specific assessments have a locational or a spatial component. And typically these days they use the error matrix to represent those errors of omission and commission, which are spatial errors, right? So we can see what's going on there. And then we can use techniques like Kappa and Margfit to better analyze those. So 2 types of analysis, and we're really going to concentrate more on site-specific assessments. So we've seen the error matrix a bunch of times now. This is the same one that you've seen over and over again. You remember that there's 3 categories, forest, water, and urban, that there's a cross classification, or this is a contingency table in statistics. And so on one axis is what the map says. We're calling that the classified data here. And on the other axis, it's what the reference data says. Okay? And we can see that the major diagonal, that area that's bolded, 28, 15, and 20 represent the agreement between what the map said and what the reference data said. Where they agreed, those things are tallied in the major diagonal. And if you add those values up, 28 plus 15 plus 20, and divide by the total number of sample units, we get 63. 63 divided by 100, because there were 100 sample units here, that would be 63%. Okay, so overall accuracy. And then we need to look at what's called producers and users accuracy, because every error has two components to it. It's like a coin. A coin has heads and tails. Spatial error has omission error and commission error. If you omit it from the correct category, you commit it into the incorrect category. And that is represented by what we call producers accuracy and users accuracy. And you can very clearly see on here, for instance, for the producer's accuracy for water, you can see that 15 times the map said it was water and the reference data agreed, okay? But you can also see that 14 times the map said it was forest when it was actually water, and once the map said it was urban when it was actually water. And so there's actually 30 water sample units on here. 15 of them we got right, so 15 out of 30, or only 50% of the time did we get it right from a producer's standpoint. Now we look at the other side of the coin, okay, from the user's standpoint, and we can see that we've actually done better. Okay, the map called it water once when it was actually forest. The map called it water 15 times when it was actually water. And the map called it water 5 times when it was actually urban, or 15 out of 21, or 71% of the time. The map called it water when it went 15 times it was actually water. Okay, so you're looking at both sides of the coin. You're looking at what got omitted from the map, but when it gets omitted from the map, it gets committed someplace else. So if it's omitted, if it's left out of the correct category, it's committed into the incorrect category. And producers and users accuracies allow us to look at those. Okay, this is why we ask people to publish their error matrices. Okay, if you look in the literature back in the late 70s, early 80s, you'll see people, showing not the whole error matrix, but maybe showing the overall accuracy, and then showing, the producer's accuracy for forest and user's accuracy for water and urban, because those were the high values. Okay, and that's not good. You want the whole matrix, one, so we can calculate whatever descriptive statistics we want, and secondly, so we can do some of the analysis techniques that we'll get to in a minute. So hopefully you have a really good understanding of the error matrix, how you calculate overall accuracy, producers and users accuracies, at this point. I've done this a couple times in these lessons, and you should feel pretty good about that. Okay, let's move on. There's things we haven't talked about at all yet, and these are some basic analysis techniques. I'm only going to talk about 2, although if you go into the literature, you'll find lots and lots of different suggestions from things. These are 2 that have been adopted pretty generally, although there is some controversy, especially over the Kappa statistic. So let's talk about them. So Margfit. Margfit is a normalization procedure. So what it allows you to do is standardize the matrix so that you can do direct comparisons. The cool thing about Margfit is that it eliminates the impact of sample size differences. And I'll show you an example in a minute that'll make that really clear what it does. Kappa allows you to do a statistical test to determine if error matrices are significantly different from each other. People have also adopted Kappa as a measure of accuracy, and it is, but that's where the controversy has occurred. So you'll see in some papers that you might read that people don't like the Kappa statistic for that reason. I like the Kappa statistic because it allows me to do this statistical test of significance. And therefore, if I come up with a new algorithm and I want to see if it's better than an older algorithm, I can do an accuracy assessment. I can run Kappa. It'll tell me that one is better than the other. And if my new algorithm is better, then I have a statistical significance test telling me that that's the case. Okay, so you'll see that Kappa especially is part of many software packages. Yeah, ArcGIS has it, ERDAS has it, lots of software packages have it. Okay. All right, so here's an example for you so we can understand what's going on. So we've got two different analysts, okay, and on the one axis is the classified data, or what their map said. On the other axis is the reference data. We've got four categories here: forest, industrial, urban, and water. And you can see that the first analyst took 391 samples. They were a little bit more aggressive, or whatever you want to say about them. They took lots of samples, okay? Whereas the second analyst, took only 246 samples. So you look at these two matrices and you want to say, okay, how do I compare these? And the fact is that you really can't at this point. How do you compare the major diagonal value of forest of 75 from analyst number 1 to 35 for analyst number 2? You can't really compare it because one took 391 samples and one took 246 samples. But as in many statistical techniques, if we normalize the data, if we use some kind of standardization, then we can do a direct comparison. Okay? And so that's what we do. That's what Margfit does for us. Margfit uses an iterative proportional fitting algorithm to make the rows and columns iteratively sum to 1. Okay? And therefore, it's standardized. And so now we can look at those individual values in each cell of the error matrix, and we could compare them directly. Okay, so did analyst number 1 do better than analyst number 2 at mapping forest? Well, it looks like they did. Analyst number 1 got about 91%, 90.8%, if you will. Maybe you don't care about all those significant digits. 91% would be fine. And analyst number 2 got about 85%. So we could say, yeah, it looks like analyst number 1's, doing a better job. Okay. We can also calculate a normalized accuracy. So you remember for just calculating overall accuracy, we would just sum up that major diagonal. So 75 plus 116 plus 96 plus 61 and divide by the total number of samples. So you can see that on the side there, 348 divided by 391, or 89%. We can do the same thing for the normalized matrix, okay, except now we know it's going to sum to 4 because the error matrix was normalized to have the rows and the columns sum to 1. So you got, your 0.98 plus 0.84 plus 0.85 plus 0.92 divided by 4, you get about an 88% normalized accuracy. For analyst number 2, we get about an 83% normalized accuracy. So that's a nice thing. We can be able to, if we have different sample sizes, we can normalize the matrix. Okay. What about Kappa? Well, what Kappa allows us to do is to test two things. One, you can test if a single matrix is better than random. That's always a nice thing to know. In other words, did I have some intelligence in my ability to make this map, or could I just have flipped a coin and labeled everything and done just as well? And if you ever get that situation, you need to go back and take another remote sensing course. That's test number 1. But test number 2 is the one I'm showing here, and that's testing if two matrices are significantly different from each other. Okay? And what that is, it uses the standard normal deviate. It uses standard statistical test, and you get a z statistic. And in this case, if the z statistic is less than 1.96, then at the 95% confidence interval, the values, the error matrices, aren't significantly different from each other. And so that's the result we get here. You can see the z statistic here is 1.67, which is less than 1.96, and therefore those two results aren't significantly different. So even though analyst number 1 got 89% and analyst number 2 got 85%. Those are not significantly different from each other. Or analyst number 1 got 88% normalized accuracy and analyst number 2 got 83% normalized accuracy. Those are not significantly different from each other. Okay, so that's the Margfit and the Kappa tests, which are very, very useful. Okay, really briefly, I just want to mention 2 advanced techniques that are sort of beyond the scope of these lessons, but I want you to just be aware of them. Okay, if you're getting to be an experienced remote sensing analyst, then you probably want to dig into these and find another source. These are covered well in my books if you're interested in from there, but you could find other sources of this as well. And that is fuzzy accuracy assessment and change detection accuracy assessment. Okay, so what are we talking about? Okay, so way back in 1992, 2 excellent scientists, Gopal and Woodcock out of Boston University, kind of proposed this idea of fuzzy accuracy assessment. They said that things are not always simply right or wrong. Okay, and so they came up with some choices in evaluating map responses where they said, let's have a number of categories here where we put some fuzziness into this, okay? Not just black and white, not just right and wrong, just some other responses. And so they came up with absolutely right, possibly right, acceptable, probably wrong, and absolutely wrong. We've modified this technique to produce a fuzzy error matrix. They didn't use an error matrix approach, and as a result, it didn't really catch on, although I think it's an excellent, excellent idea. We adopted their ideas into a fuzzy error matrix approach, and here's what we did. There are now 2 values in the off-diagonal elements of the matrix. And so instead of having those responses that Gopal and Woodcock had, we have 3 possible responses. We have the one that we think is right, the ones that we think are acceptable, and the ones that we think are wrong. Okay? And so what happens is the major diagonal is still the ones that we think are right. Okay? But the off-diagonal elements, the first value in the off-diagonal elements is the ones that we would accept, and then the second number in the off-diagonal element is the ones that are still wrong, that are poor or unacceptable. Okay? And so that allows us to have an error matrix and then do some additional calculations. Okay? We've set this up. Again, here's the 3 categories: good, acceptable, poor, or not acceptable, or unacceptable. And we've done this in a computerized field form. And so you can see the classification scheme we're using is right there. Okay? And you can see you've got a choice for all the categories on the map. You know, which one is good, which ones are acceptable, and which ones are poor. And in this particular case, it was easy because it was water. Water was the only acceptable answer. It was only good answer. There was really no other acceptables besides the good water, and everything else was poor. Okay, but you can imagine an example where, sparse or barren or sparse vegetation versus grassland. You know, the density of the grass. You might say, well, I really think it's barren, so that's my good answer, but I would accept grassland and I wouldn't accept anything else. Okay, and so you were able to indicate the goods, if there are any acceptables, and then the poors. And then when you do that, you get an error matrix that looks like this. Okay, so you can remember that the off-diagonal elements, the first value are the acceptables and the second value are the unacceptables. And the major diagonal, which is in green here, the first value is the goods, and then you can ignore that other value. This was in an Excel spreadsheet and it was hard not to be consistent. Okay, the cool thing about this is that you can still calculate the traditional statistics, the traditional overall accuracy, producers and users accuracy. You just use the major diagonal and divide by the row or column total, depending on whether you're talking about producer or user accuracy, or just sum the major diagonal and divide by the total. So we call those the deterministic accuracies now. And then you can also calculate fuzzy accuracy. Okay, what do you do with fuzzy accuracy? Well, with fuzzy accuracy, you count not just the major diagonal, but the values in the first set of the off diagonals. Okay, so you would take the value in the major diagonal and you would add the values in the first part of the off diagonal, the acceptables, okay, and add those all together and then divide by the total and get a new fuzzy overall accuracy. So you can see that the deterministic overall accuracy is 151 divided by 321, or 47%. You can also see that the fuzzy accuracy is 236 over 321, or 73.5%. Okay? And the same thing's true for producers and users accuracy. You can see the calculations there. What's being added is not just the major diagonal, but the first values in the off diagonal elements. Okay, so you can see for deciduous forest, initially it was 48 divided by the total, which was 56, or 85.7%. But if you're going to do the fuzzy, you can see that you're going to take the 4 from the evergreen forest. You're going to take the 2 from the scrub shrub. You're not going to take that 1 from the grassland because that's an unacceptable. You're not going to take the 1 from agriculture other because that's an unacceptable. So you have 48 plus 4 plus 2, so 54 divided by 56, or a fuzzy logic of 96.4%. Okay? So some people go, well, that's just cheating. And I can understand your argument there. But if you go out into the field, or especially if you're doing this where you're collecting the reference data from imagery and it's really hard to tell, and as the classes get more and more similar or got more and more complex, then fuzziness makes a lot of sense. Okay, so just be aware of this. This is a technique that we use regularly, especially in classification schemes where we have 50 or 60 map classes. It makes a whole lot of sense. The second method I want to talk about is the change detection accuracy assessment. And as you well are aware, change detection can get very, very, very complicated. There's a wide variety of ways to do change detection. The big problems with doing change detection accuracy assessment is, how do you get the reference data? Can I travel back in time to collect that reference data? Well, certainly you can't go to the field in 1976 if it's 2020. Okay, not going to happen. Okay, so you got to use other imagery or whatever you have to get that reference data. So that's a big problem. The other issue that people tend to forget about is that change is a rare event, and so you have to sample specifically for a rare event. If you just do some kind of a random sample and 5% of the area has changed, then 95% of your reference samples are going to be collected in the non-change area. And you're not going to have enough samples to know anything about the change detection areas. Okay, and so that's a big deal. You have to really pay attention to that. Sample for a rare event. And lastly, change detection requires that you use a change detection error matrix. And a change detection error matrix becomes very, very complex. Why? Well, look to the right, and you can see that if I have a 3-category single date error matrix, I've got 3 categories, A, B, and C. And on one axis, I have the reference data, and on the other axis, I have the map. Well, if I go to change detection, I don't have a 3x3 error matrix anymore. I actually have a 9x9 error matrix. Again, on the one axis, I have the reference data, and on the other axis, I have what the map says. But now I have what it is in time 1 and what it is in time 2. Okay, so for the map, I have that it was A in time 1 and also A in time 2, or A in time 1, B in time 2, or A in time 1, C in time 2, or B in time 1, A in time 2. You see the point? Okay, and so however many map classes you have to square that to get the size of the change detection error matrix. Okay, so remember, you've got a 3x3 single date error matrix. I need 50 samples per map class, so I need about 150 samples to do the accuracy assessment for that single date. Now I've got 3 classes. How many samples do I need for my reference data for a change detection? Well, It's got 3 classes, but that means 9 different possibilities. Okay, so now I need 450 samples to do an accuracy assessment of just a simple 3-class change. Ooh, what if I have 10 classes? It's not uncommon to have 10 classes. Okay, 10 classes means 100 classes in my change detection error matrix. 100 times 50 is 5,000. Uh-oh, I'm in really big trouble here, right? Okay, so what's the solution to that? Well, we can rearrange the change detection error matrix a little bit. You can see all I've done is grouped it so that I've got the no change area in the upper left, and then the change area in the lower right, and then, so that's really the major diagonal, right? And then I've got the change no change and the no change in the off diagonal elements. Okay, and so maybe I can collapse it down to a change no change error matrix that you see at the bottom here and just get enough samples for that. Also, one thing that helps us out is that, let's say it's a 10-year mapping change period. Okay, some things aren't going to change between that 10-year period. You're not going to go from buildings to forest in 10 years. You might go from forest to buildings in 10 years, but you're not going to do, you know, the opposite typically. Okay, so there's some of those samples that we can cross out. So anyway, important to understand these 2 techniques, or at least be aware of them if you get to that point in your career that you need to either think about fuzzy accuracy assessment, how that might help you out, or if you're starting to look at change analysis, which is obviously a big component of remote sensing. All right, so summary here. So I asked you a favor, please help me out. Don't use the word ground truth. I would really appreciate that. We discussed different types of analysis. We looked at non-site specific and site specific assessments. We reviewed to make sure that you understood how to get the descriptive statistics overall, producers and users accuracies from the error matrix. I presented Margfit and Kappa, 2 pretty powerful techniques that allow you to do some additional analysis in your error matrix once you've got it, and made sure that you understand that there are other techniques as well. And then very, very quickly, I tried to introduce 2 other additional techniques that I thought were very important for you to have a feel for: fuzzy and change detection accuracy assessment. So thanks for coming along on this lesson, and we've got 1 more to go. Thanks.